Alright, just going to look at a few examples here from 2.9. You don't have too many homework problems, I don't think, from 2.9, but we'll take a look at a few examples. I want to start with number 11, so let me draw the graph of that. And it looks something like this. So the first thing we want to determine, this is a graph of the derivative f prime of a continuous function. So this is f prime. This is the derivative. So the first thing we want to say is, or answer is in part A, is where is f increasing or decreasing? So let's first of all start with f increasing. Well, f is going to be increasing wherever its derivative is positive. Remember, if the function is going up, the derivative is positive because the slope of the line tangent will be positive. So it's going to be increasing where f prime is positive. That's going to be between 0 and 2. It's positive there, and then also between 2 and, or rather 4 and 6, and also from 8 on out to infinity, as near as we can tell anyway. The function is going to be positive there. Where is f decreasing? Well, it's decreasing wherever the derivative is negative, which is going to be between 2 and 4, and also between 6 and 8. Alright, let's look at part B. What values of x does f have a local maximum or minimum? Well, local maxes and mins are going to be at the smallest point on the graph or the largest point on the graph. And you can see that we have a local minimum right here at x equals, actually, let me start that over. This is the derivative, f prime. So the derivative corresponds, when the derivative is equal to 0, that's where we're going to have local maxes and mins, because that's where our function is going to be making its turn. If you think about what the graph of the original might look like, it's positive here, so it's increasing, and it's 0 here, so it makes a turn, then it's decreasing, and then it's 0 here at 4, so it makes a turn, and so on. So we're going to have local maxes and mins any place our derivative is equal to 0. Here it's decreasing until it becomes 0 and becomes increasing. This point lines up here. So any place where our derivative is equal to 0 is where we're going to have local maxes and mins. So at 2, 4, and 8, those are the three places where our derivative is 0. Those are the three places where we could have maxes or mins. We could also have a 0. We could also have a local max or min where the function is undefined, and you can see that's going to be at 6. So 6 is a possibility because the function is undefined there. Now, which is local max and which is a local min? Well, you can see we're going to have a local max at 2 here and also at 6. One thing that might be happening here at 6, we have a cusp where the function is continuous, but the derivative is not defined at 6. So notice that our derivative has a hole at 6. So it's not defined there. And here we would have an increasing function getting positive, positive, then all of a sudden it's very negative very quickly. So we're going to have a max at, a local max, it looks like, at 2 of these critical points of 2 and 6, and we'll have a local min, it looks like, at 4 and 8. Because at 4 here, that corresponds to this point, we were decreasing because the function derivative was negative, hit 0, and the derivative goes positive, so decreasing, 0, increasing. Alright, and also 8, we're negative on the derivative, then positive, so decreasing, 0, increasing. Alright, let's look at part C. Part C asks us to determine where it's concave upward or concave downward. Well, that's going to be where the second derivative is greater than 0 is going to be concave upward. So second derivative greater than 0, that's going to be concave up. So that means we're looking at the derivative of f prime. Where is that going to be positive? Well, it's going to be positive where f prime is increasing. F prime is increasing between, well, from 3 on up, and it's still going up here, increasing on up from 6 to infinity. So we're going to be concave up, again, where the function, where the derivative is increasing. Because where the derivative is increasing, f prime, that's where the second derivative is going to be positive. So here we are. F prime is increasing here from 3 to 6, and then we have a jump here, so then it's increasing again. F prime is increasing again from 6 to infinity. So that's where we are concave up. Now, where is f double prime less than 0, which implies that we are concave down? Well, the second derivative will be negative when the first derivative is decreasing. And the first derivative is decreasing from 0 on out to 3, and looks like that's the only interval that we can see where the function is decreasing. Okay, and then part D. Part D, we are asked to state the x-coordinates of the points of inflection. Remember, the point of inflection is where our second derivative is going to be 0. Where the second derivative, so in other words, that's where we're going to change from a decreasing function to an increasing function. where the derivative of f prime is going to be 0. There's one place where the derivative of f prime is going to be 0, and that's where x is equal to 3, because the line tangent to f prime here is 0. So that's where we change from concave down to concave up for the original function f, where f prime is decreasing to where f prime is increasing. And finally, part E, we want to sketch the graph assuming that f of 0 equals 0. Well, this graph is valid here, but it doesn't have f of 0 equaling 0. Let's just shift it up. Remember we said we can shift an antiderivative up or down, and so let's do it like this. And we're going to come up here. We have a little max here at 2, and then we have a min at 4, and then we have a cusp here, sharp turn, and then it comes down. We have again a min at 8, and then we increase like so. So that blue graph there is a possible graph of f, given that the red is f prime. Next problem we want to look at is number 18. We're asked to sketch a graph of a function that satisfies all these conditions. We want the derivative at 1 and the derivative at negative 1 to be 0. That means the function is going to turn at those points. We want the derivative to be negative anytime the absolute value of x is less than 1. So that's going to be between negative 1 and 1. That's all we mean there. When x is between negative 1 and 1, that's the absolute value of x is less than 1. If the absolute value of x is between 1 and 2, we want the derivative to be positive. The absolute value of x is between 1 and 2, so that's going to be between 1 and 2 or between negative 1 and negative 2. And the derivative is going to be negative 1 if we are outside of 2. The second derivative we want to be negative between negative 2 and 0. So we've got basically some sections here that we can divide this thing up into. And let's just make it nice and big. 1, 2, negative 1, negative 2. Alright, here's what we want. We want f prime of 1, f prime of negative 1 to be 0. That means we're going to have turning points at these 2 points at negative 1 and 1. Well, let's not draw that in yet because we're not sure which way we're going to be turning. We do know that f prime of x, we want that to be negative if the absolute value of x is less than 1. So between negative 1 and 1, we want the derivative to be negative. That means we want the function to be decreasing. So this means that f is decreasing in this section. So we could do something like this. Function's decreasing in this section. Okay, so now we can see since the function's decreasing in this section, we're going to want to make it turn this way and make it turn this way so that f prime of 1 is 0 and f prime of negative 1 is 0. The lines tangent there are horizontal lines. Let's see, we want the derivative to be positive if the absolute value of x is between 1 and 2. So that means the function's increasing when x is between 1 and 2. Also, we actually want the function to be increasing between negative 1 and negative 2, because here the absolute value of x is between 1 and 2. So I spoke a little too soon there. We're actually going to want to flatten out, so the derivative is 0, but I want the derivative to be positive. So I want, oh no, that's okay. We're going to be increasing here then when the absolute value of x is between 1 and 2. So if x is negative 1.5, the absolute value of that is positive 1.5. So this section here applies. We're increasing in this section when x is between negative 1 and negative 2, and also when x is between positive 1 and positive 2. We want f prime of x to equal negative 1 if the absolute value of x is bigger than 2. So that means that we're going to basically, when the absolute value of x is bigger than 2, we want it to be a negative 1, the derivative, so it's going to be we want the same slope all the way through. We're going to have a straight line coming like this. We're going to have a straight line coming like this with a slope of negative 1, because any value of x where the absolute value is bigger than 2, so that means anything to the right of positive 2, anything to the left of negative 2, we want to have have a slope of negative 1. So we'll just have a line with a slope of negative 1 here. That way our derivative is going to be that exact same slope. So we can connect those like that and like that. Lastly, we want the second derivative to be negative if we're between negative 2 and 0. So that means we want to be concave down between negative 2 and 0, and we don't exactly have that. So we're going to have to change over here a little bit. What we're going to have to do, we want to be concave down between negative 2 and 0 and keep everything the same. So we want to be spilling water in this section here, between negative 2 and 0, and that'll do it right there. But remember, once we get to the left of 2, we want our derivative to be negative 1, so it's going to come down like this. And what we're going to end up having to have here is a cusp, where the derivative is not going to be defined at -2. So we're going to have a cusp or a corner here where we make a sharp turn like that to make sure that this is all concave down between -2 and 0, but we still have a slope here of -1. That might be a little steep, but the slope here is also -1 for anything bigger than 2. We can have this smooth turn here. That's okay. Inflection point at 0, 1, so that's this point right here. We'll just say this is 1. This inflection point right here, that's where we change from being concave down to being concave up. So there's a possible graph for all those conditions for f of x. Finally, I want to look at number 25, where we're given a graph of a function f, and we want to find out which graph is an antiderivative of f and why. So, which graph could be an antiderivative? In other words, which graph is a function f such that f prime is equal to f? So another way to ask it is f is a derivative of which function? Alright, so we want a function f so that the derivative is equal to f. Well, let's see, what's our relationship between our original function and our derivative? So if we want f is increasing, then f prime, which is equal to f, is positive. If f is decreasing, then f prime, which is what we want to be little f, has to be negative, in negative territory. And let's see, if f has a max or a min, then f, which is equal to f prime, is equal to 0 or possibly undefined. Alright, well, let's see what's going on with f. Where is f positive? F changes from positive to negative right here. It's negative between 0 and this mark, and it's positive from this mark on out. Alright, so which function is increasing from 0 to this point and decreasing from that point on out? Well, it seems like there's only one, and that's going to be function c. If we let this be f, then the derivative of this function, let's see, it's going to be, oh, wait a minute. That's not right, is it? That's not right. Okay, let's start over here. Don't worry about anything, we'll be okay. We're looking for where it is f, where is f positive, where is f negative. F is positive to the right of this mark, negative to the left of this mark. Where f is positive, that means the original function must be increasing. So let's see. Well, b is increasing to the right of this point. C is not, so b is a possibility. To the left of this point here, you can see the original function f is in negative territory, so we want the function whose derivative is f to be decreasing. And that is true also for b. b is decreasing until we get to this point. Here, the line tangent has a slope of 0, and then b is increasing here, so its derivative, which is f, is going to be in positive territory. So f is equal to graph b. The graph of b is a possible antiderivative for little f, because if you took the derivative of b, measured the slopes here at each point along b, and graphed those slopes as y values, you would get, in fact, the graph of f. Okay, so that's it for 2.9. Let's get your password. And the password for this 2.9 homework is going to be transpicious. TRANSPICUOUS. And that, of course, means clearly seen through or understood. So I hope that Chapter 2 has been transpicious for you, that you understand it completely. And if you don't, make sure you ask me some questions about it.